Now let's look at capacitors in series, and then we'll combine the two and deal with combination circuits. That is, circuits with both capacitors in parallel and in series. But let's first look at capacitors in series, and we'll have a few rules. Let me just remind you of the rules for capacitors in parallel before we move on, though. For capacitors in parallel, we had a couple of different rules. One, they have the same voltage. Capacitors in parallel all have the same voltage. Two, the equivalent capacitance, excuse me, it should be C equivalent. The equivalent capacitance is just the algebraic sum, C1 plus C2 plus however many capacitors you have. And then 3, Q is equal to CV. So we'll just sort of take those three rules. Some others will sort of crop up as we go along, but let's just take those. Now we're going to have similar rules for capacitors in series, so they'll be similar but different, obviously. All right, so capacitors in series all have the same charge. This is one of our first rules. Remember, capacitors in parallel have the same voltage, but capacitors in series have the same charge. So if I imagine this setup here, I have two capacitors in series. You know, I put a certain amount of charge here, plus Q, due to the battery. And then that causes the same charge, but negative, to be placed there. Now what I have here is this induced charge. Remember we had induced charges where we could set up these charges without actually touching anything? Well, notice that in a capacitor, there is no touching here. There is no flow of electricity because nothing's touching. This is a completely isolated portion of the circuit right here because it's not touching. Now normally, you know, we have insulators here, but that does the same effect as causing that to be an isolated part of the circuit. All right, so if I have minus Q here, that means that I have to have plus Q here. All right, and then that's going to cause minus Q to be right there. So that results in the fact that the capacitors in series are all going to have the same charge, and that's going to be sort of our first rule. Now the equivalent capacitance for capacitors in series is given here. It's 1 over C1 plus 1 over C2 plus 1 over C3. Plus however many capacitors you have. And so, for example, let's say that I have two capacitors here, a 3 and a 6 microfarad. If I wanted to calculate the equivalent capacitance, I would just say 1 over 3 plus 1 over 6. And that's going to be equal to that's 1 over 2/6 plus 1/6. That's 1 over 3/6, which is 1 over a half, which is 2 microfarads. So here I have an equivalent capacitance of 2 microfarads. On the test and what have you, I'll try to have simple numbers that you can just do in your head, but you also need to just sometimes you'll see more complicated numbers that you can't do the math in your head. So you should make sure that you know how to do this type of operation in your calculator. It's not a common thing that I take the inverse of this sum of these fractions. All right, so just make sure in the homework that you practice that, just to make sure that you got the mechanics of it down. All right, let's work through an example. Oh, and then also the charge that is found on that equivalent capacitance is also found on either of the two capacitors. So for example here, let's say that I had a voltage equal to 12 volts. All right, that would mean that I would have a charge over here of 24 microcoulombs. Right, Q is equal to CV. That's true for any capacitor. And so if I have 24 microcoulombs there, I'm going to have 24 microcoulombs here and here. That was rule 1, that charges and capacitors in series have the same charge. Let's do an example. In this circuit, what is the potential difference across C1 and C2? The first thing I want to do is find the equivalent capacitance. And so I'm going to do 1 over 2 plus 1 over 4. See, that's 2/4 plus 1/4 is 3/4. That's 1 over 3/4, which is 4/3, or 1.333. We'll just call it 1.3 microfarads. So I can write my equivalent circuit. It's going to be 1.3 microfarads. Now, Actually, I'm going to write this as 4/3. You can do it in decimal form if you like, but I'm going to do it as 4/3, which is the same as 1.3. So that's my equivalent circuit. And now I can find the charge since the capacitors in series, they all have the same charge. And so I had an 8 volt Q is equal to C times V. I had 4/3 microfarads, that's my capacitance, that's my equivalent capacitance, and I had 8 volts. And so that is 32/3 microcoulombs. So that's the charge on each of the capacitors. If I go back and look at this circuit, I have 32/3 of a microcoulomb here, and 32/3 of a microcoulomb here. I have the same charge on each of those capacitors as what I had here. I also had 32/3 of a microcoulomb here, which was just 8 volts times the capacitance, which gives me the amount of charge on that capacitor. Okay, so now we can find the potential. Remember, Q is equal to CV. So V then is equal to Q over C. On these problems, anytime you get two of the values, you can always find the third. All right, so V is equal to Q over C. Q is 32/3. Our C, this is C1 and Q1. C1 was 2 microfarads. That was from the original problem. So that is 16/3 volts. And V2 is going to be Q2 over C2. Q2 is the same as Q1, that's 32/3 microcoulombs divided by 4 microfarads, and that's going to be 8/3 volts. All right, so those are V1 and V2. So notice here that C1, which has half the capacitance of C2, you know, C1 was 2 microfarads and C2 was 4 microfarads. It has half the capacitance, but it has twice the potential difference. Twice the voltage of C2. Notice it had 16/3, and this only had 8/3. Okay. Also, and this is going to be a little rule here, so we'll count this as a rule, that when electrical devices are in series, the sum of their potentials is equal to the total source of the potential. The sum of their potentials equals the total of the source potential. So here we have 16/3 and 8/3. Let's just add those up and see what we get. 16/3 plus 8/3 volts. That's going to be V1 plus V2. Is going to be 24/3 volts, which is equal to 8 volts. If we go back and look at our circuit, look, we had 8 volts. So here I had, let's see, V1 was 16/3. And this was 8/3 volts. All right, but they add up to equal the total, which was 8 volts. That's the total source potential. We'll see more of that in just a bit. All right, let's just sort of review those rules. So these were the rules. Where are they? These were the rules that we had for caps in parallel. They had the same voltage, that's their equivalent capacitance, and Q is equal to CV. For caps in series, we have a set of similar rules. And I'll reiterate these as we go along, but just want to sort of hammer these into your mind. First, caps in series have the same charge. They have the same charge. For caps in series, the equivalent capacitance is equal to 1 over 1 over C1 plus 1 over C2 plus however many capacitors you have. 3, for capacitors in series, the total voltage equals the sum of the individual voltages of the capacitors in series. And then 4, this still applies that Q is equal to CV. That still applies. All right. So those are the rules for capacitors in series. Now next we're going to move on to capacitors in combination circuits where we have a combination of series and parallel. And I think you also have a question here. Yeah, here's a nice little simple quick test question. Want to know what is the potential across this 24 microfarad capacitor?